Hello everyone. For this tutorial video, I'd like to discuss change of variables for double and triple integrals, as well as for multivariable integrals in general. In particular, if we recall the substitution rule from Calculus 1, the integral from a to b of function of g of x times the derivative of g of x, integrated with respect to x, equals the limits of integration changed with respect to u, function of u with respect to change in u rather than change in x. And this was also called u substitution for this reason. We bring this up because we use a similar, although not exact, thought process to computing multivariable integrals. A specific example to demonstrate what I am talking about is, if we want to transform the ellipse r equals x squared plus y squared over 36 equals 1, with x equals u over 2 and y equals 3 times v. We would do this by simply substituting in what we are given for x and y, and then simplifying the transformation using techniques from algebra. And we conclude that we have u squared plus v squared equals 4, or a disk, aka a circle, of radius 2 after we have done the transformation. We will next investigate a general formula for the change of variables of a double integral, which is known as the Jacobian, after the mathematician who first established the change of base formula for double integrals. In particular, if we have x is a function of u comma v and y is another function but a separate one of u comma v, then the ratio of these two functions is exactly equal to a matrix, or more specifically, its determinant, which requires us to be familiar with what a determinant is before we compute it. The determinant of a matrix of the form A in the top corner, B in the top right corner, C in the bottom left corner, and D in the bottom right corner is A times D minus B times C always, as long as the matrix has this number of entries in this exact order. So now we can use this fact to simplify the Jacobian as change of x over change of u times change of y over change of v minus change of x over change of v times change of y over change in u. So now we can prove explicitly that the polar coordinate formula is the way it is by doing x equals r times cosine of angle, y equals r times sine of angle, doing the ratio of the function x comma y over r comma angle equals the Jacobian matrix of change of x over change of r in the top left corner, change of x over change of angle in the top right corner, change of y over change of r in the bottom left corner, and change of y over change in angle in the bottom right corner. We now compute these partial derivatives, and then use the determinant formula given earlier. So when we do this, we get r as our final answer for the Jacobian. So now we conclude that change in area equals this Jacobian times change of r times change of angle, and we substitute in r for the Jacobian because that's what we found it to be. And we conclude that the change in 2D area is exactly this, which is what we saw by the geometric proof, but it never hurts to double check. It should follow that if we have a triple integral instead, then the Jacobian would be change of x comma y comma z over change of u comma v comma w equals the determinant of a 3 by 3 matrix rather than a 2 by 2 matrix. So now we can use this to give a comprehensive proof of the spherical coordinate formula for triple integrals. And we see the Jacobian evaluates to negative magnitude squared times sine of phi after we exhaustively compute the determinant of this 3 by 3 matrix. And so we see that the change in volume equals this Jacobian times change of magnitude times change of theta times change of phi. In the next video, we will discuss surface area involving integrals, but more general formula instead of specifically rotate objects around an axis like we saw earlier. Don't forget to subscribe if you found this video informative, and make sure to see the other tutorial videos, and follow me on either Facebook or Twitter for more content.